Okay, first order, first degree. First order, first degree differential. Yeah, differential equations. Yeah. Word problem. Radioactivity. Yeah. Radioactivity. Yeah. Alright. Here we go. Let's start. Are you ready? I'm ready. Alright. So you have D. This is really cool. You gotta set it up. Set it up. You gotta set it up. D N D T for time equals K N. We got variables up in here. Alright? So you let NO be the original amount. The original amount of what? The original amount, man. The original amount. Alright? Say you're trying to look at a rock. Alright? There's a rock or a piece of wood or something like that. And you say, oh my goodness, that is 67, that is 73.4%. 74.3% of it, of carbon 14, the concentration. You know what I'm saying? You look at the rock and the concentration of carbon 14 is at 73.4%. You're like, dang. It's not 100%, 73.4%. Alright, that's one variable. I'll be plugging that in soon. Alright, but anyway, we're back here. We're back here. N is the amount present at any time. So the amount present at any time. Alright. So we've established that. And T equals time in years. Alright, so we got some stuff down. We got some stuff written down here. And it takes carbon 14 about 5,730 years. It takes it 5,730 years to go one half life, one half of an original amount. So you take the original amount of it or whatever, and a neutron will fly off in 5,730 years. A neutron will change into a proton, or vice versa. It'll decay. It'll take that long, 5,730 years. Alright, so that's the premise. So, we have dN over dt equals kn. Alright, first thing you want to do, you want to separate the variables, alright? So you got to separate the variables. So we have this, we put a little algebra in here. So that's that right there. You know, you can rewrite it, but I'm just going to look at it. I'm going to look at that right there and say, hey, I want to take dt, see a dt? Put it over here, put it right here. See that? And then that cancels out. So you're left with dN equals kn dt. And you're like, I want to continue to go on this algebraic, you know, this algebraic mission, you know? So from here, you're like, okay, there's an n. N, put an n over here. These n's cross out. And you're like, well, look at this. Shouldn't this n cross out? And you're like, dang, what do I do now? You don't do anything. Look at this. It's dn over n equals k dt. Alright, so you're good. You're golden right now. So, you're good right now. You got that down. Now you're going to throw in some logarithms. So we're going to go back up here. This is when it gets tricky. A general solution is, you know, logarithm n equals kt plus logarithm c. The c, you know, that's just how it is. Alright? So we're going up here, all this let no crap. So logarithm no is equal to k o plus the logarithm c. There's that c again. What is c? c is equal to n over 0. Man, this Sharpie is starting to smell, you know what I'm saying? Alright, we we're going to move this up or whatever so we can get some room up in here. All right, so we got C equals n 0 or whatever, you know what I'm saying? So right here, you're like, what do I do now? So you have logarithm n is equal to k t plus logarithm n o. And we're starting to break some stuff down. You know what I'm saying? L n oh my goodness. Let's go to the next page right here. Let's just go to the top of it. Top of it. Ugh. L n, you with me? Minus. See, we did a little algebraic here. See that right there? So Ln minus Ln NO equals KT. See how you take the plus, you just throw that over here or whatever and just said it's like that. And then you're like, well, we got the logarithm, so it is the logarithm n over, you know, this is just what you do, over NO. See, it's the logarithm. It's just, they just go to there. N over, and then don't forget about your K and T. Alright, you with me? So now we're here. And don't forget, now what the whole thing here is, we're using a condition of 1/2 of carbon-14 decays in 5,730 years. So we have, which gives us like N equals NO divided by 2. Alright, the half-life, when T equals 5,730. We already did it up there. Alright. Alright, we'll just do T equals 5,730. Alright. Oh man. Alright, so this gives us a really cool, something really cool. NO over 2 is equal to NO, and here comes, look at that. Oh, look at this. You remember this stuff? I remember it. Look at that. See that? We just plugged in the numbers, and from there, we just, you know, see that? We just plugged in the numbers, and don't forget. Just don't ever forget. So we have N equals NO every half-life 1 and then 5,730. Isn't that amazing? I think that's amazing. We're starting to get a little tricky up in here, you know what I'm saying? Gonna have to move this up, move it up. Up. Alright, that gave us some more room. Alright, where we at? Okay, so we solved this right here, which gives us N equals 0.734 NO. Amazing. So N, yeah. So you have 0.734 NO. Now, this right here is 73.4% from up there. So we're just plugging it in here. Alright. So we plug that in. So 0.734 NO is equal to NO, there's that half-life, plus, oh my bad, T divided by, a little tricky, 5,730. I had to think a little bit. So you have a logarithm of 0.734 is equal to logarithm 0.5 T 5,730. Alright? So T is equal to 5,730 logarithm 0.734, 73.4% over logarithm, there's that half-life, 0.5. And you plug that into your calculator and you get 2,556 years old. A couple, depends on what calculator you have and how you got it set, but it'll be in that ballpark. So that's how old using the radioactive methods we did here to figure out how old that rock is, you know what I'm saying? So that's what we did, and if you want to find anything much older than that, you have to do some other radioactive testings and stuff like that. So this is the first order, first degree differential equations of radioactivity. Radioactive elements, they decay at a rate that is proportional to the amount of the element present. So I'd like to thank you, and thank you.